Welcome. This video is going to talk about the mass transfer equation. This is an equation that describes how stuff moves from one area to another. Specifically, imagine you've got yourself a cup of coffee, and maybe there's some coffee beans in it like that, or even more likely coffee grounds in a filter. We've talked about in class that there are a whole bunch of things in coffee beans. There's lots of different chemical compounds. When you put them in water, some of them will start moving out of the coffee bean and into the water. Of course, this process will continue until equilibrium is reached and the concentration in the water in the coffee cup is the same as the concentration of the stuff that's in the coffee bean right there. But what this transfer equation deals with is trying to describe how does that rate change over time. Now, it might look somewhat familiar to you, because Mr. Newton, Dr. Newton, I should say, came up with something very similar that we talked about in class, his law of cooling. So it turns out that the rate of mass transfer is proportional to what the concentration would be when the solution is saturated. That means when there's no more ability of the solution to hold anything. And we can subtract from that the concentration at any particular time, t. So the astute among you might realize that as this and this get closer to each other, that is, the concentration gets closer to the saturation concentration, this side of the equation goes toward 0, and that would mean that the rate would slow down as well. So this means that there is some sort of change that is happening in the rate as the concentration changes. Some of you might realize that this is the beginning of a differential equation. We've got ourselves a function. Let's see if we can get the derivative in there. Let me rewrite this a little bit so that we can see what's going on. It turns out, as is the case in many things, that to take our proportionality and turn it into an equation, we have to add a constant. Let's call that constant k, because a lot of times when we have a constant, that's what we call it. There's CSAT minus c at a particular time, t, like that. And this k, just like the coefficient of drag or the cooling constant, depends on a lot of things. It depends on the original concentration of coffee to water ratio. It depends on the temperature. It depends on the shape of the material. It depends on how finely ground it is. So that K takes quite a lot in. But let's focus on what this rate is over here. I can rewrite this a little bit differently. The rate of mass transfer is how much mass is transferred per unit time, like that. So let's put this side back in there. That's the C at the concentration at a particular time. If we wanted to be a little bit more calculus-y about it, and we wanted to get a very small change in mass and a very small change in time, we could replace the deltas with a D. And now we've got ourselves, well, almost a differential equation. We do have a function in it. We know that the concentration is going to be changing over time, but we don't have the derivative of that function yet. So you may recall that mass is frequently inconvenient. So when we were, for example, doing the equations where we took little slices of water and emptied them out of a tank, finding the mass of that individual little slice of water is kind of inconvenient. So let's see if we can mess around with mass a little bit. It turns out that concentration is how much mass you add to something and how much volume it takes up. So you might imagine that if you had a large mass of sugar and you added it to a small volume of water, the concentration of that sugar water would be very high. We can reorganize this if we care to, and we can get mass equal to C times V. So let's replace that and see what we get. On the top then, we have dCV divided by dt, and over here we still have K CSAT minus C at a particular time, like that. Now we've got ourselves a differential equation. We've got a function, and then its derivative over here. We can tidy this up a little bit, though, if we make an assumption, and this is kind of a big assumption, but it works for our purposes. We're going to assume that the volume doesn't change and that it's a constant. We can therefore pull it out in front. So we could say this, dC dt, that's very clearly the concentration at any particular time, like that, changing. The volume as a constant equals K C sat minus C as a function of time, like that. So here we have, as before, our function, and now very clearly the derivative, just like that. So this is a differential equation. Our class doesn't really get into solving differential equations, but we can get some information out of it. If, for example, let me just get these out of there so you don't need to be bothered by them. If we assume that the volume is staying constant, which in reality it wouldn't, because when you add sugar to water, for example, the volume of the liquid does actually go up, the mass does not disappear. But if we assume that that's a constant, and we assume that k is a constant, which is fair, we can make a proportionality out of this before we solve that differential equation. So let me do that for you. If we just assume then that dc as a function of time, dt, equals c sat minus c at a particular time, we can see what happens and see how this is borne out, right? So as time goes on, essentially, that will get closer to that, and therefore this will get closer to 0. And that makes sense that then the rate of mass transfer would also get closer to 0. I put an equal sign in here when I meant to put a proportionality sign. It's no longer equal to because I took out the constants. So this makes good sense, that as the time goes on, the concentration goes up, approaches the saturation concentration, and then we end up with a very slow rate. So if we solve this differential equation, which we don't have the tools to do, but if we did, we would find this. So here's the solution to that differential equation. I need a dot on my I right there. If we do it, we get this. That's the concentration at any particular time divided by the saturation concentration. So the concentration, if we let the thing go for an infinity number of seconds, it reached a dynamic equilibrium. There it is. That's the solution. This is really clever because now armed with this information, instead of doing a whole bunch of trials, we can just do one trial, find out what K is, find out what C sat is, and then we'll be able to figure out what the concentration will be at any particular time. Let's check to make sure that this still makes sense. If we have time get bigger, then we know the exponent that the E is raised to gets to be a bigger negative number, therefore E gets smaller, and then we're taking a smaller and smaller and smaller thing and subtracting it from, or something closer to 1 and subtracting it from 1. That side's going to, I said that wrong, I'm sorry. We're subtracting something and smaller from 1, so that side is turning into 1, which means the relationship between that and that is getting close to 1. That means that, well, as the concentration goes up, the rate goes down, and it goes down according to this natural log exponential thing. So if we were to draw it, if we were going to draw the concentration as a function of time on this axis and the time on this axis, we would find it would do something like this and approach some asymptote. So this is really useful because once we get one run of data, we can kind of figure out what the saturation concentration might be by looking at the maximum things it reaches, at what time it gets there, and then simply plug it into this equation and we can figure out anything that we need. This went by rather quickly. We'll talk a little bit more about it in class on Monday.